Welcome to both AP Bio and Honors Chemistry students and some of those who are in both. This is our scientific method experimental design presentation, and again, showing it to both. For AP Bio, the reason we're starting with experimental design is it's a key component of the exam. One of your long free response and a number of different situational questions in the multiple choice deal with experimental design. It's just, and this fits for our honors chemistry student. It's, if you understand experimental design, your understanding of what's going on with a lab, why it is or isn't working, hypothesis and analysis, scientific, everything we do in science, from analysis to then designing your own, to making changes, to doing whatever. It's just important to have the background. It's a key scientific component. That's why you've kind of heard about it or learned it before, and we'll see it many times again. And again, I'll go back to AP Bio, especially. If you know the stuff, then you can look at a lab and you could look at data, analyze data, determine what the hypothesis was, what was the question they were answering, etc. Anyhow, let's do some basic background. First, what's a scientific method? And I'm not going to go into deep detail because we've seen this before and you're bright folks, but it's the process where scientists try to construct it, get accurate representation or data. And it's a process with 6 steps. And what are they? Number 1, you're asking a question. Okay. Something that you want to research or experiment or find or do whatever. Second, you do some background research. Now, these things I give you, we're not doing that in a sense on our own, but then you do background research so that you can design a well-done experiment. And then you construct a hypothesis. And you've heard this before, and you just say if then. But let's get more detail, because one of the areas that young science students are not great at is writing a hypothesis, constructing the hypothesis. So you want to formulate a hypothesis to explain whatever the experiment is testing and what you believe will be the outcome. If the, and this is what's different than probably what you've had in the past, if the, and that's where your independent variable comes in. We'll be talking about independent variables in a minute. If the independent variable is modified in this way, so whatever treatment you're doing for the experiment, then this will happen to the dependent variable. And I think it would be very enlightening, very beneficial for all students to think that in a hypothesis, the if is related to the independent variable, and the this or the then is the dependent variable, used to predict the existence of other phenomena or predict the results of new observations. Okay. Then you test your hypothesis by doing an experiment, and that's where our experimental design comes in, and it leads to either confirming of the hypothesis or ruling out the hypothesis. And again, a hypothesis is never right or wrong. It's just supported or not supported. And folks who design a poor experiment may not match a hypothesis that actually could be a correct hypothesis, but the data doesn't support it because they had a poorly designed lab. See what I'm saying? So we never say right or wrong, we just support or not support. And then, of course, you test, and then you analyze your data, you draw conclusions, you report your results. And truly in the scientific method, if I was going to, before reporting results, if you didn't match, you might go back in, in the real world, after you got analyzed your data, you might go back if it didn't fully support or if things were kind of screwy, you might go back and tweak the experiment a little bit and try it again and try it again until whatever. And then all that can be reported in your results. Okay. Anyhow, the testing by doing experimental design. And this is the key of that we want to talk about for both classes. You're both going to be responsible for this, both Honors Chem and AP Bio. For AP Bio, it's going to be particularly important for working on your AP exam questions. So an experiment deliberately imposes a treatment, a change on a group of objects or subjects in the interest of observing the response. That's the treatment. Okay. Quick question, what's the difference between an experimental design and observational study? An observational study just involves collecting and analyzing data without changing existing conditions. In AP Bio, your home range activity is kind of like that. An experiment deliberately imposes a treatment, a change on a group of objects or subjects in the interest of observing the response. For Honors Chem kids, the density labs we're doing are more observational studies, although you're analyzing data and stuff like that. You're not doing anything to change we're not doing anything to alter the situation. You're doing observational data collection. Okay. Experimental design, we are concerned with the analysis of data generated from an experiment. That's the key. If you design it right, you get good data and you can make a more accurate analysis and hypothesis. It is wise to take time and effort to organize the experiment properly to ensure that the right type of data and enough of it is available to answer the questions of interest as clearly and efficiently as possible. This process is what's called experimental design. What is a treatment? A treatment is something that researchers do to experimental units. For example, you can take a cornfield, divide it into 4. Each part is treated with a different fertilizer to see which produces the most corn. Okay. The specific questions that the experiment is intended to answer must be clearly identified before carrying out the experiment. We should also attempt to identify known or expected sources of variability in the experimental unit, since one of the main aims of a designed experiment is to reduce the effect of variability on the answers to the questions. In an ideal world, you would have only one variable, the independent variable, changing. Everything else would be constant and steady. It's the ideal. Doesn't always work that way. It's not always possible, especially when doing studies with human and living organisms. It's not always possible to control everything, but you can control many. Anyhow, you design experiments in order to improve the precision. Now, what are those sources of variability? And for high school kids, number 1 is the very first one, experimental bias, the favoring of certain outcomes over others. For some reason, high school students may have never seen a lab before, but they get data and they go, we're wrong. They have no idea what's supposed to be going on, but they go, we think we did it wrong. We think we did it all. They're already making projections. Let the data do the speaking. That's not saying that you might not see things going on during the lab where you go, huh. But let the experiment be the experiment. You don't want to choose something. You don't want to have a bias and try and push it towards the direction you want to go. Another one is placebo effect. Since many patients are confident that treatment will positively affect them, they react to controlled treatment, which actually has no physical effect at all, such as a sugar pill. And that's often done in drug studies and medical studies and stuff like that. A group will get the actual drug and a group will just get a placebo. Nobody knows who's getting what, so you can sometimes see an effect where the people believe so strongly that they, and sometimes you can go with bias. They can start saying, hey, I feel better, even if they don't. Okay. How do you eliminate that variability? Number 1, double-blind experiments, most preferred. Then neither the experimenters nor the subjects are aware of who's getting what. And that leads to, that eliminates bias, essentially, because nobody knows who's getting what. Okay. And also that placebo effect. Since nobody knows who's getting what, experiment or whatever, then it also allows those who are getting the placebo not to think, just to think, I don't know if I got the right one or not. So include control or placebo groups in experiments to evaluate the difference between the regular. That's why they do it. And in a double blind, that takes away some of the mental, not all of it, but some of the mental. Okay, randomization. Another way to eliminate objects or individuals are randomly assigned by chance to an experimental group. Using randomization is the most reliable method of creating a homogeneous treatment group without involving any potential bias or judgments. And then replication. A repetition of experiment on a large group of subjects is required. If a treatment is truly effective, the long-term averaging will reflect it. So if you are ever designing something, okay, try and make, however you assign things, make it random. Honestly, have somebody else do it, make it double blind random with the control groups, and you repeat a number of times. And I will tell my AP Bio folks that when you are writing things on the AP exam, there's one area that folks often forget, and that's telling how many times you will perform the experiment. Okay, now what are the different groups? Well, we talked about a control group. That is your baseline measure. So for our Digital Learning Academy kids in AP Bio, the control group is in your mustard seed germination, the one you just set aside and do nothing to. Identical to all the other items or subjects that you're examining, with the exception it does not receive the treatment or get manipulated that the treatment group does. Okay, that's your baseline on the side. Example, when examining test tubes for catalytic reactions of enzymes when added to a specific substrate, the control test tube would be identical to all other tubes with the exception it won't have the enzyme. So then you can compare it to the ones that do get the enzyme. Okay. For our AP Bio kids, and I'm sorry, honors kids, for making it up, but they do a little more experimental design than you do, so I'm sorry that I keep mentioning them. But for those cohort A and B who are going to be here in the sodium alginate, the first thing we're going to do is we practice using the sodium alginate yeast spheres is going to be the control. And then you'll be coming up with a change for what we're doing. Okay, treatment groups is the item or the subject that is being manipulated. In our example of the catalyst, all other test tubes containing the enzyme would be part of the treatment. And then what are the variables? And these are key. An element, feature, or factor that is liable to vary or change. So there's three categories: independent, dependent, and the control. The independent is what's varied during the experiment. It is what the investigator thinks will affect the dependent variable. Okay. And so as we talked about before, that's the very first part of the hypothesis, if blah, blah, blah. For example, the investigator may want to study coffee bean growth. Possible independent variables could be how much fertilizer you give them, the type of fertilizer you give them, the temperature that they're at, the amount of water they get, the day length, the amount of light they get. All of these things may affect the number of beans, weight of the plant, leaf area, plant height. There's all sorts of things. The dependent variable is what will be measured. It's what the investigator thinks will be affected by the experiment. So again, if we go to this coffee bean growth, possible dependent variables are number of beans produced by the plant, the weight of the plant, the surface area of the leaves, the time to full maturation, the height it gets to. Okay. So the independent variable would have been things like the amount of water. The dependent variable was the height or the full maturation of the plant. Okay. Key. Since you need to know which factors affecting the dependent variable, and this is some of your background research, there may be only one independent variable. The investigator must choose the one that he or she thinks is the most important. But the scientist can measure as many dependent variables as he or she thinks are important. So you only have one independent variable, but in a coffee bean thing, you could measure height, weight, but you could measure every dependent variable you want and look for changes. Okay. And then a control, that's where the variables are held constant. We've talked about that. Since the investigator wants to study the effect of one particular independent variable, the possibility that other factors are affecting the outcome must be eliminated. So for example, the above scientists must ascertain that no differences in the type of fertilizer used exist, or amount of water, or variations in temperature or day length exist. Keep it under control. You can't have the amount of light per day changing constantly. Okay? And then let's talk about data. There's a couple ways. There's qualitative and quantitative. Qualitative really is observational. This is a word or quality of subject measure other than a number. So odor, color, texture, taste, things like that. Okay? We will be doing a lot of qualitative stuff, Honors Chem, initially. And then we move into quantitative. Quantitative is the number. It's measured stuff, distance, mass, volume, density. And we will be doing some quantitative Honors Chem right away with our density lab right away. But then we'll also have a lot of qualitative. Okay. Now, in making data tables, it's amazing how you say make a data table and young folks struggle. And for Honors Bio, there's often a graphing problem off your data tables or something like that. So just know this. One, your title of your data table, it should identify both the independent and the dependent variable. The independent variable then goes on the x-axis, the dependent on the y-axis, in a sense, and then calculations are generally off to the right. So your labels on top are your anyhow, you label the independent variable stuff on top, and then the dependent variable numbers come down. Not a big deal. Most of you know how to do a data table. And then graphing. This, Honors AP Bio kids, graphs. You will be graphing stuff. And interpreting graphs, and they want graphs completely labeled and everything else. Sorry, got a little goofy. And we'll also do a lot of graphs for Honors Chem. So graphs are great for quantitative data. There are two kinds of graphs. Really, there's one graph. Line graphs are the only graphs out there. Anything else is a chart. And we'll maybe take a minute we'll maybe take a point at each as we get more and more in each class, as we get more and more into using data, as to when do you do both or when do you do either. Sorry. But the key is the only real graph is a line graph. Everything else is a chart. Okay? Just trust me on this one. All graphs include in the title, and notice it's very much like your data table, the effect of the independent variable on the dependent variable. Notice that all the words in the title are capitalized except for prepositions. Okay. The y-axis then is your dependent variable that it will include its labels, units of measures, appropriate scale to fit the data, and the full range of, if you're doing this hand on graph paper, you use the full range, because the bigger the graph, the less variable you iron out some of the anomalies that can happen. And consistent increments. The x-axis is the independent variable, labels, units of measure, appropriate scale, and consistent increments. And then for a key for data series. Okay. But the first three, absolutely important in the AP Bio exam. And important for Honors Chem when you have to turn in a graph too. Okay. So line graphs, essentially you're comparing data, relationship between variables. Bar chart, and I just crossed out graphs to kind of illustrate. Bar charts are used to show comparison of multiple objects, like things here on every day of the week. Okay. Essentially comparing a number to a word. 99% of the time you're going to do a line graph, no matter which class of mind you're in. On a rare occasion, AP Bio, a question may have you do a chart or a histogram, but we'll address that as need be. Okay. And then remember, as you are graphing, line graphs, especially important for honors chem here, the relationships between variables. The first graph on the top is direct. As x increases, y increases. The second one, indirect or inverse. As x increases, y decreases. And then constant. As x increases, y maintains, it stays the same. Okay. And the conclusion. The concluding paragraph, 5 to 8 sentences, it all just depends. Should include the following not numbered. Number 1, restate your problem. What were you doing? Okay. What were you researching? What were you experimenting on? What was your purpose? Then restate the hypothesis, if then. Then you write that you're going to accept or reject the hypothesis discussed. Okay. Using the analysis of your data. So you have to put in data in your analysis. That is your analysis. Number 4, include a discussion of the validity of your results. That's your error. Okay. And then how might this be improved or modified to further test the problem and get even more accurate results? And then a summarize or restate of a quick conclusion written in the third person. So what was your purpose? What was the hypothesis? Okay. Do you accept or reject it? This is your analysis portion where you use your data to support or not support. What error did you have? What might be a next step in the process or modifying the experiment? And then a summary statement. Okay. There you go. There's the exciting world of experimental design. And we'll be working with that in both classes. So hope you enjoyed this video. We'll talk to you again soon.